Today, we are going to present Lab 1 for the FPGA design, which is about the 7-segment counter. The members of this group are Nur Rashidah binti Muhammad FAUZI, Nur NAZIFA binti Cik SAMSURIA, and Rashidah binti AMINURRASHID, which is myself. Boards from the Altera DE2 series have long been employed in the advancement of education. The new technology, Altera DE2115 Cyclone 4 series boards, offer an optimal balance of low cost, low power consumption, and a rich source of logical function, memory storage, and DSP capabilities. This is the mostly utilized field programmable gate arrays (FPGA) devices for educational growth in the fields of electrical and computer science. Counters are used in electronics to tally the events on each pulse of input that is received. The oldest method of displaying counter values is using 7-segment displays, which are still in use today. The display's LEDs are placed so that the decimal digit 8 is created. When the input pin receives the signal, the corresponding LED illuminates and can show decimal numbers from 0 to 9. The objectives of this experiment are, first, to understand the basic design flow by using DE2115 board and Quartus 2 software. Second, to design a simple half adder with VHDL, schematic block diagram, and waveform. And the last one is to design a counter with frequency divider by using the 7-segment on DE2115 board. In this presentation video, I will explain on the task 1 of this lab, which is about the half adder. For method of task 1, the first step is to write coding of half adder in a VHDL file using the Quartus 2 software. The second step is to compile the coding until the full compilation was successful statement appears, as shown in the figure. The third step is to create the schematic block diagram of half adder, which consists of XOR and AND gate in a block diagram or schematic file. Then, the block diagram is also compiled successfully. The fifth step is to create the waveform of half adder in UniVST program BF file, which is a type of file provided in the Quartus 2 software. The final step is to simulate the created waveform and record the resulting waveform. This is the overall flowchart of completing task 1, which is the half adder. First, we write the coding of half adder in a VHDL file and compile it. If not compiled successfully, then we need to rewrite the coding and recompile until it is successful. Then we create the schematic block diagram of half adder and also compile it. Same case with the first step. If the block diagram is not compiled successfully, then the block diagram need to be recreated. Next, we create the half adder waveform by inserting the input and output pins. Then we simulate the waveform and record the resulting waveform. Lastly, we verify the resulting waveform by comparing it with the half adder truth table. If it is not the same, then the waveform needs to be recreated again. Now, I am going to explain the coding for task 1, which is half adder. So here, the first 2 lines are to define the library package, which is IEEE, and library file used, which is IEEE.std_logic_1164.org. So basically, this coding is divided into 2 parts, which are entity and architecture. Here, I am going to explain the entity part, which is from line 3 until line 7 of the coding. So entity here, function, is to define the input ports, which are A and B, and output ports, which are sum and carry out. For the architecture part, from line 8 until line 12, the function is to define the functionality of chip, which is in this coding, sum port is assigned to be the operation A XOR with B, and carry out port is assigned to be the operation of A and with B. Next, I'm going to explain on the result of task 1, which is half adder. So here, the top figure shows the resulting waveform of half adder. To verify, the waveform must be compared with the truth table of half adder, and the logic operation involved for half adder is A XOR with B and A and B. So to compare, we can refer to the top figure here, at the dotted line here. We can see that the carry out and sum value is 0, which is corresponding to the first row here, which is when the input A and B is 0, the sum and carry out will also be 0. Next, refer to the top figure here, the blue, at the blue dotted line. We can see that the value of sum is equal to 1 and the value of carry out is equal to 0 when A is equal to 0 and B is equal to 1. And this is corresponding to the second row of the truth table. Next, we refer to the orange dotted line. We can see that the value of sum is equal to 1 and the value of carry out is equal to 0 when A is equal to 1 and B is equal to 0. And this is corresponding with the third row of the truth table here. Lastly, refer to the green dotted line here. We can see that the value of sum is equal to 0 and value of carry out equals to 1 when A and B both are equal to 1, and this is corresponding to the last row of the truth table here. So here we can verify that the output waveform is correct as it is corresponding to the truth table of half adder.
My name is NAZIFA binti Cik SAMSURIA, matrix number 11919A1. I will explain task 2 7-segment counter. Method and flow diagram for task 2 7-segment counter. Method of task 2. Firstly, this task is named 7-segment counter. These 6 folders are created named as divide time, divide 50, clock gen, clock counter, set deck, and count 0099. Then, new project in wizard is opened. Quarters 4E DE2115297 board is selected. Divide 10, divide 50, and clock gen are designed and completed. The schematic block diagram for clock gen is designed. Clock counter, set deck, and count 0099 are designed and completed. Next, wire bond layout are created after all 6 codings have been verified and pin or not assignment is set for the signals defined in the coding. After computing the pin planner based on the position in the DE2115 user menu book, the count 0099 code is programmed into the DE2115 board by clicking the program device. After that, the USB blaster is clicked at the hardware setup. Then, add file is clicked and put the count0099.sof file into it. Next, the button start is clicked to start upload program into the hardware. Lastly, the output at 7 segments is observed. Flow diagram based on the method of task 2. This is overall picture of 7-segment counter process.
My name is Rashidah binti FAUZI. My matrix number is 1191980. So first, I will explain about the coding that used in task 2, which is the 7-segment counter. For coding divide 10, we have entity and architecture. The entity name is a divide underscore 10, which is in line number 4 until line number 7. The input port is clock in and the output port is divide 10. Then we have the architecture of divide 10, which is start from line number 8 until line number 23. We use structural coding for this architecture, and then we first assign the signal, which is B, which is range 0 to 10. We need to assign the signal before we begin the process. And then the process of clock in is start. If the clock in event is equal to 1, then B will be B plus 1. If B equal to 5, divide 10 will become 1. If B equal to 10, divide 10 will become 0 and B equal to 0. Then the process is end. This is for the process of clock in. Next, for coding divide 15, we also have the entity and the architecture. The entity name is a divide 15, which is start from line number 4 until line number 7. The input port is clock and the output port is divide 15. For the architecture, we use the structural coding. And as usual, we need to define or assign the signal, which is before starting the process. The signal is assigned to be which range 0 to 15, and then the process of clock is start. Next, if the clock event is equal to 1, then B will be B plus 1. But if the B equal to 25, divide 10 will become 1. As if B equal to 15, divide 10 will become 0 and B will become 0. Then the process is end. Coding for the clock gen, so we have the entity name as a clock gen, which is start from line number 4 until line number 15. For the input port is clock in and the output port is a frequency of 10 Hz, 1 Hz, 100 Hz, 1 kHz, 10 kHz and 100 kHz. For the architecture of clock gen, we are using the structural coding. In line 17, we use the component. So if we are using the component, we need to do a declaration. Same goes as the entity declaration, which is we have the input port of clock and the output port which is divide 15. Then the signal are defined from line number 27 until line 32. Next, each frequency is assigned to its synthesized wire. There are 7 port maps that have been computed, and then a port map tells how a design entity is connected in the enclosing architecture.
This is block diagram of clock gen. One block diagram for divide 50 at the input of clock in. Block diagram of divide 50 is connected to 6 block diagrams of divide 10 as their inputs. Outputs from the block diagrams of divide 10 are all different in terms of frequency value: 100 kHz, 10 kHz, 1 kHz, 100 Hz, 10 Hz, and 1 Hz. This is coding for clock counter. The input port is clock in and the output port is Q. The signal is assigned to B and X. If the clock in even and clock in is equal to 0, then B will be B plus 1. If B is equal to 9, then B will become 0, 0, 0, 0. Then Q is equal to B. Other than B is equal to 9, Q is equal to B. Then the process is N. This coding is for set that the input port is C and the output port is hex 0D. This process is using case statement. When 4 bits number is executed, the output will be 8 bits. There are 10 times the 4 bits input have executed from 0000 until 1001, which represent 0 until 9 in decimal. Other than that, hex O underscore D will give output 1111, 1111. Then the process is N. This coding is for count 0099. Input clock in, output hex 0, hex 1, hex 3, and hex 2. The architecture is structural coding. There are 3 parts of component statements, which are clock gen, set deck, and clock counter. The signal is assigned to clock input, Q0, Q1, Q2, and Q3. There are 9 components instantiation statements, which is U1 is equal to clock gen, means speed is equal to 100 Hz. Then, set deck and clock counter come by pairing about 4 times, which represent digit unit, digit 10, digit 100, and digit 1000. Then the process of BDF type is N.
Next is the result that we get from the task 277 counter. First, we have got the wire bond layout after successfully verify all the seed coding. Next, we get the pin and node assignment for the signal defined in the coding. So, the purpose of this pin and node assignment is to get the correct output when we embedded the coding inside the board. So, the 7-segment counter will show or display the correct number from 0 to 9. Which is the output will be the right number. So I will show the result in board when we use 1 Hz. You can see that the speed is very slow. Next we do for the modification for 100 Hz. It show a little bit fast. And then for the 100 kHz, it is very fast. So basically, by implementing the higher frequency of clock, which is we do 100 kHz, the speed of the 7-segment counter will be more faster compared to the 1 Hz and 100 Hz. So this statement can be related to the formula of T equal to 1 over frequency, which is frequency is the rate of repetitive event, while the T is the period of a repetitive event. So the formula above is time is inversely proportional to the frequency. Hence, if the higher the frequency, it will give the lower time. And a clock in a FPGA system is a driving FPGA architecture and determining how fast it can run and process the data. Clock in FPGA is determines how fast a flip-flop or group of a flip-flop run. Next, the discussion for the task 277 counter. For question 1, we have already implemented the counter at high and low frequency clock and already show the output for the 7-segment counter. So basically, when we want to have a very fast clock, and then we need to put the highest frequency and vice versa.
Question 2. Explain why component instantiation and process statements are used in count 0099. Component instantiation is used to define the behavior of how the components are connected to each other. Process statements used to create combinational logic and also used to describe algorithm. For question 3, explain the process statement in set deck and clock counter. For set deck, process statement use case statement to define a 7-segment display decoder, while in clock counter, process statement use S statement for condition of output Q and signal B.
So basically, as a conclusion, we can see that students manage to have a deep understanding and learn more widely about the concept of half adder and 7-segment counter. Other than that, this lab also gives the opportunity to the student to observe about the concept learning in FPGA subject by using software of Quartz 2 and hardware board of DE2115. Other than that, students also managed to compute all the coding and make some analysis of the output and make some discussion about the outputs. Last but not least, thank you very much for listening and spend your time for our presentation. We also hope that our presentation already give a clear explanation about the half adder and 7-7 counter concept. Thank you very much.